Okay. Okay, thank you. Thank you. This is a joint work together with Renato Masiani from the architecture section of our structural engineer department in Rome. And I will talk about some new micromechanical estimates of the interaction energy for shape memory alloys. So of course there's a large number of micromechanical models for shape memory alloys. There's a large literature that various models differ for different level of approximation of the microstructure. For us, there is a large group of models pioneered by Partout and Berveillet that uses a multi-phase microstructure, and of course, when there is a one-phase fraction for each Martensite variant. But there is also another group of models which it's very bad. Yeah, it's very bad resolution. Sorry. Anyway, other models that uses a two-phase microstructure, which is a close approximation for single crystals, but anyway can use also for polycrystals, provided the transformation is interpreted in some average way. So I will focus on this second group of models, in this model there is of course only one phase fraction, and of course the two transformations are modeled by increasing or decreasing phase fraction that I'll indicate with C. Just to fix notation, wow, it's very bad. Just to fix notation, I will start with stress-based free energy. Just to fix notation, let me see that I'm using sigma as a macroscopic stress. M bar is the effective elastic compliance, and E star is the macroscopic transformation strain. W star is the interaction energy, which is the main object of our discussion. Then, of course, there is the part of chemical free energy, where there is contribution for the effective specific heat, and then the thermal contribution, which is given by the austenite-Martensite entropy difference and the austenite-Martensite equilibrium temperature, which is the temperature at which the two phases have the same free energy. Just very standard, just to fix notation. So this is basic ingredient of microscopic model. Of course, given free energy, this determines the driving force, and the driving force, of course, has two important contributions, one for chemical free energy and one for the interaction energy that I renamed by simplified notation W1 prime and C bar. Okay, then of course driving force is used to set up transformation criteria, where driving forces is put equal to some driving force threshold, that threshold that I call the capital lambda, and of course there's different expression for the two transformation. Of course we have the four transformation criteria for activation and completion on forward and reverse transformation. Okay, just very, very standard. Then, of course, the rate of energy dissipation is just the product of the driving force and the rate of change of internal variables. And, of course, second law enforces non-negativity of this. And then this is as a consequence that the values of the driving force threshold at the start and the beginning of forward and reverse transformation must have definite sign restrictions. Of course, the one for forward transformation must be non-negative, and the other one for reverse must be non-positive. And that's, of course, very important and very obvious. Anyway, so I would like to point out now that this very simple consideration allows one to find very simple but very stringent bounds about the interaction energy, about more precisely the derivative of the interaction energy, because it's enough to write down the transformation criteria in stress-free conditions. Then, of course, the stress part goes down, and then it's just a kind of balance between the threshold, the derivative of the interaction energy, and the one of the chemical free energy. That's the criteria. Then, of course, by second law, we have sign restriction of this on this term, this threshold. And then, of course, this immediately gives inequality on the free energy derivative in C equals 0 and C equals 1. Very, 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 very simple. Then, of course, taking into account the various sign conditions which are on the real parameters, for example, the the difference in entropy is negative value, then equilibrium temperatures can be expressed in terms of transformation temperatures, and the standard transformation temperature are like this, ordered in this way. MF, MS, AS, and AF are the standard transformation temperature for shared memory. And taking into account this, we get very simple but very stringent bounds dictated only by the second law on the derivatives of the interaction energy evaluated at extreme values of the phase fraction. So W1 of 0 is bounded by this chemical free energy that depends on the difference between AS and MS, the two transformations. Okay. To our knowledge, I think that this kind of bounds are not being stressed so much in the literature, and then turns out to be also very important. So, as a motivating example, I would like to show you that the interaction energy that are derived by using some standard micromechanical models tend to violate these bounds. In many cases, and then I should we just choose one example, some very classical experimental data about a single crystal of nickel titanium, which are at two different temperatures. So this just note the order of magnitude of transformation stresses. At these two temperatures, the transformation stresses are about 500 and a little bit more than 600 megapascal, just for future reference. Then, of course, of this material we know the main parameters. We know the active variant by the crystallographic parameters. We know then by the crystallographic parameter we know the local transformation strain tensor, and then we can immediately compute the bound for the derivatives of the free energy. I've written there. And then if you consider a standard model, a micromechanical model, a very simple micromechanical model like Mori-Tanaka for random distribution of inclusion in isotropic metrics like this, which has been used by several authors, it is immediate to compute. If you compute this derivative, then immediately you find that these bounds are largely violated. And let's see what are some consequences of that. If you try to compute the driving force threshold for activation of forward transformation, then you find that the threshold is negative. It's negative. Whereas the second law, of course, requires it to be non-negative. And what are the consequences for this? The consequence is that if you reject this and usually you use the minimal possible threshold for forward transformation, which is 0, if you use 0 and you try to compute the forward transformation stresses, then you get very high stresses, which are more than the double of the observed one, which is kind of important. And analogous results you can obtain with other model, other materials, other criteria. We did a lot of experiments. So that's the motivation. So in this work we propose a way to obtain a smaller interaction, because all this phenomenon is due to the fact that these micromechanical models tend to overestimate interaction energy. So interaction energy usually is too big in many of the models. So we are trying to propose a way to get lower interaction energy in such a way to be consistent with those bounds. So let me just briefly review some general expression about interaction energy that can be obtained by considering a representative volume element of just simple linear elastic phases subject to some given eigenstrains. And then in this context you can easily define interaction energy and macroscopic transformation strain, and everything depends on what? Everything depends on the average stresses and average strain in the various phases under a traction-free boundary. That's also standard. And another standard result is that under homogeneous boundary condition, this average stress and strains can be expressed in terms of transformation concentration tensor, which is FRS. So as soon as you know if you know these tensors, you can compute everything. In particular, if you use a two-phase microstructure, this is simplifies a lot. These are the expressions for interaction energy and for microscopic angle strain. Then in the two-phase microstructure, there are lots of simplification because the transformation concentration tensor can be expressed in terms of mechanical concentration tensors, which are in turn are related to the effective stiffness or compliance. And then, of course, if we define this tensor here, which is closely related to the difference between the effective compliance and the average compliance, then you can have a simple expression of the mechanical concentration tensor and the transformation concentration tensor. Then, if you substitute, then we get immediately very simple and very general for two-phase microstructure expression for interaction energy and macroscopic transformation strain. The importance of this is that we express the interaction energy as a function of the effective compliance. So whenever you have a model for the effective compliance, then we have a corresponding estimate for the interaction energy and for the macroscopic transformation strain. So by these relations, we can test any estimate. There are a large number of estimates in the literature of composite materials and so on. So that's the most important connection. Then what we tried? We tried to do this. Among the large number of models, we selected a model proposed by Dvorak, which is called the average field approximation, very simple in principle, and we show that while this is often used for composite material, this model are very useful feature for shape memory materials for interaction energy. Okay, this IFA, the effective compliance, just given by this expression where you have these two tensors, but finally depends on what? Finally depends on S0, where S0 is the SLB tensor in an average comparison material, because the idea of this model is to compute average stress and strains in the various phases by embedding them in a comparison material which has a stiffness, elastic properties that can be adjusted, getting different estimates. And the comparison materials in turn is subject to some suitable average stress and strain in order to model in an indirect way the interactions. And of course it is well known that this scheme yields as a special case Mori-Tanaka, H-6 bound, or even self-consistent, depending on what kind of comparison material you use. Okay, of course in the two phases this simplifies a lot, and then of course it's rather straightforward to determine the expression of the effective elastic moduli, and to show some result, simple result, we focus on the special case of isotropic material, and then the estimate of the effective elastic moduli as in terms of the phase fraction as this structure, and if we use the SLB tensor for spherical inclusions, then we found this expression in terms of four non-dimensional parameters. In terms of four non-dimensional parameters, which are important. Two of them are written there. So we wrote all of this in terms of alpha 0 and beta 0, which are the ratio of the elastic moduli of the comparison material with respect to the matrix. Phase 1 is austenite in this case, so in a sense can be considered as a matrix in this case. And alpha 2 is, in a sense, is the ratio between the elastic moduli of the two phases that represent elastic heterogeneity. So that's just the standard expression for effective elastic moduli. So given the connection I showed you before, whenever we have this estimate for effective compliance, we immediately have a corresponding estimate for the interaction energy for the shape memory material. Of course, in an isotropic case, the interaction energy is split in a volumetric part, but and in a deviatory part, which is the most important because local transformation strains in this material usually tends to be purely deviatoric in most cases, not all. And that's this simple expression for the interaction energy. There's a remarkable aspect is that if this expression has a non-trivial homogeneous limit. Homogeneous in what sense? So if we if we neglect the elastic heterogeneity, namely we consider the two phases with the same elastic properties, this still has a non-trivial limit, which is this one. And in turn, this limit, as a further special case, taking the comparison material equal to the matrix 1, so the austenite, gives the Mori-Tanaka, the well-known Mori-Tanaka expression. So this is useful because in several contexts it may be useful to neglect elastic heterogeneity. Okay, now this scheme by Dvorak in the composite material, the comparison material is used to approximate the effective stiffness. In this case, for shared memory, this can be interpreted in a different way because the comparison material and the stiffness of comparison material we can interpret this as a model of the accommodation phenomena that take place around the inclusions, and therefore we can use the variation of the stiffness of the comparison material as a model of all such a complex phenomena that can take place around inclusions. And therefore, if we plot the interaction energy, in particular this is the deviatory component of the interaction energy as a function of the phase fraction here, from 0 to 1, and here as a function of the ratio of the comparison material over the matrix, you see that this parameter here is important because here is a comparison material which is stiffer than the matrix. Here at 1 is equal to the matrix, and then decreasing the stiffness of the comparison material, we see really interaction energy going down. So we see that the stiffness of the comparison material is decreasing and is gives us the possibility to obtain smaller and smaller interaction energy. Here you see at this parameter 1, this is Mori-Tanaka, and then of course we can obtain smaller and smaller parameters by reducing the stiffness of this comparison material. Of course, similar estimates are possible for microscopic transformation strain, but I will not use them. And then of course I'm finishing. We can go further. We can even compute an explicit expression of the driving force which is consistent with this micromechanical model in an explicit way. And then the driving force pi is divided in 4 contributions. One is due to the transformation work. One is the 2 contribution from the interaction energy. Then there is the thermal term, and then there is a term related to the elastic heterogeneity. And then here in this general expression for driving force, the micromechanics enter through a simple, very specific places by this expression. Then of course there is the problem. So how to interpret the stiffness of this comparison material? By adjusting, but it's very simple and immediate to compute an upper bound for this stiffness, because we can immediately identify what is the maximal stiffness that permits to comply with the bounds that I mentioned before. So it's rather easy to write down the stress-free transformation criteria as a function of alpha 0. Alpha 0 is the ratio of the stiffness of the comparison material, and you can even easily solve for the value, setting the threshold, driving force threshold to 0, which is the minimum value. You can immediately take this, and this is an upper bound. This is the maximum stiffness that the comparison material can have before violating this thermodynamical bound I showed you before. So this is kind of the interesting result. So in conclusion, we have just applied this procedure based by this Dvorak approximate field average field approximation models, and we show that they are very useful properties to derive expression for the interaction energy, because they contain this parameter. We can adjust this parameter of the comparison material stiffness in order to find interaction energy that comply with thermomechanical bound, and we were able also to find an upper bound for this stiffness of the comparison material. Okay, and that's enough.
I have one. The Dvorak scheme is sometimes said to be too stiff for the effective stiffness. Is it a problem in your case, or?
Not really, because here we are using in a different way. Because here we are not using this scheme to approximate the effective stiffness on an elastic material. We are saying more. We are saying that in shape memory, the purely elastic model is not enough, because if you consider the material really elastic, any purely elastic material, it's enough. So we are interpreting this comparison material also going outside the bound, because Dvorak gives also the bound for the comparison material, but we are not interested in this because we are modeling a different phenomenology. So in a sense we are using this as a kind of microscale damage. This stiffness reduction is a kind of microscale damage. So of course we are going outside this.